Okay, so for the final thing from section 3.3, we need to talk about the greatest integer function. The greatest integer function is a specific function that has business applications. It's a little different. It's a type of piecewise function that has its own kind of formula. It's given right here. When you see this, f of x equals, and then there are these little brackets, double brackets of x, that's called the greatest integer function. And basically what it does is any number you put in for x, it turns it into an integer. What's an integer? An integer is, okay, I'll give you some examples. You tell me if they're integers. 7.
Yeah.
Negative 7. 4.2. No. 5.7. 2/3. 0.
Yes.
Okay, so you know the difference between an integer and a non-integer, right? Any number you substitute in for x, it turns it into an integer. And the integer it turns it into is the greatest integer less than or equal to the number you substitute in. So think about that for a minute. It's the greatest integer less than or equal to. So we'll just kind of make a little table and talk about it real quick. If I have my x's and my y's, let's say I substitute in 0. That's already an integer, agreed? So the greatest integer function leaves that alone. It stays 0. But what if I put in 1/2 or 0.5? If I substitute in 0.5 or 1/2, that's not an integer. But this function maps that to the nearest integer below it. Not above it. It doesn't round it up, it rounds it down to the nearest integer. So what's the closest integer to 0.5 but that's not bigger than it? 0. So it maps it to 0. How about 0.75? 0. How about 0.8? In fact, it stays that until I hit what number? 1. And when I hit 1, its y values jump up to 1. And then they stay 1 for 1.2, 1.3, 1.8. Any of those, they're 1. Where's it going to jump again?
2.
At 2. As soon as I put 2 in for x, it's going to jump up to 2. So everything between 2 and 3 stays 2. Once you hit 3, it jumps to 3. Does that kind of make sense for what's going on there? Now, where people get into trouble with the greatest integer function are the negative values. The negative values, let's talk about those for a minute. I'm going to kind of make a new table over here just to kind of talk through it. Let's say I put in -1. What's that going to give me? What's the closest integer less than or equal to -1? If it's an integer, it stays.
Oh, -1.
So it stays -1. So everybody's okay there. Here's the question though. Where does -1.5 go? Does it go to -2 or -1? It goes to the greatest integer that's less than or equal to it. So less than -1.5 is -2. So people have a little bit of trouble with the negative. So that's where we're going to spend most of our time is talking about this. So let's just take a look at what the graph of the greatest integer of x looks like. The greatest integer of x. I'm going to make this as big as I can so that we can kind of see it a little bit better. Well, first off, we're going to go ahead and we're going to kind of talk about it, just what we know. If I put 0 for x, what does it give me? 0. So we agree there's a dot there, right? What if I put in 1 for x? What does it give me? 1. So 1, 1. What if I put in 2? 2. So do you agree that all of these dots where the x and the y are equal are going to be on this graph? Everybody agrees with that? Okay. So far, this is what we have. And we can make a table, but we just did that on the previous slide. So I'm going to take a minute to kind of think about it from a graphical standpoint. What about -1? If I put -1 in for x, it's going to stay -1, -2 will map to -2, -3 to -3. Is that enough for now? Okay. Now the question is, what's happening in between the integers. So if we think about what's happening between here and here, all of those numbers are going to 0 or to 1. Like 1/2, what does that go to? 0, because the greatest integer less than or equal to 1/2 is 0. 0.7. So everything between 0 and 1 will map down and produce a y value of 0. Now what we do to show that it jumps here is you put an open circle on that end to show it's all 0 until I actually hit 1, then it jumps to 1. Okay, so it's actually going to make these little pieces, just little pieces that kind of look like dumbbells right here. All right, now let's hop up here. We know at 1 it's 1. What about 1.2? Is it 1 or 2?
1.
1. 1.3?
1.
1.4?
1.
1.5? 1.6? 1.9?
1.
2. 2 goes to 2. So everything between 1 and 2 is 1. But the minute I hit 2, it jumps. What do you think everything between 2 and 3 will equal? 2. So these will stay, and then it'll jump. These will stay, and it will jump. These will stay, and it will jump. So it's producing these little bitty pieces of a graph, and they're called stair steps sometimes, stair step functions. And this is actually the way the postal service works. They charge you a certain amount, up to a certain amount, then it jumps up, and they charge you another amount based on the weight. Yes? It's typically how things in the past have been priced for the post office. I think now in the day and age of computers, though, they actually can charge you a different amount for every weight because it can just churn it out real fast. But for a long time, it was a very set step function, sort of like the greatest integer function that determined that. Which way do you think this goes? Okay, let's talk about it. Negative 1/2. Right here. Does it stay here or does it jump down to negative 1? Yeah. So negative 1/2 is negative 1. Negative 0.2 is negative 1. So it maintains that same pattern. So if you can establish a pattern for the positives, you can see the pattern for the negatives as well. And it's just going to continue. Everything between negative 1 and negative 2 is going to go to negative 2. And that would just continue forever. And that's the greatest integer function, just kind of in a nutshell. So here we have a printing company, and they're going to charge you $10 for every order, no matter what. Even if you order nothing, they're going to charge you $10. Then they're going to charge you $20 for each box of 200 forms. But they're going to count any portion of a box as a full box. Make sense? Okay, what do we want to let it be our x's? Our x's are going to be our number of boxes. Yeah? Number of boxes or a number of copies, or what's it going to be, guys? Does it matter? No? So y'all want to do it boxes, or do you want to do it by copies? Boxes? Okay. So we're going to count by ones. So these are going to be our boxes. So this would be 1 box, 2 boxes, 3 boxes, 4 boxes, 5 boxes, 6 boxes, 7 boxes. Agreed? Okay, so we've decided we can count by ones there. Now, if we counted by copies, how much would this be? 200, 400, 600, 800, 1,000. So if we did by copies, our scale would look a little different, but it would basically still represent the same thing. Agreed? Okay. Now let's talk about our money. Let's let money be over here. So money, I think we should count by, do y'all want to count by 10s or 20s? 10's okay with you?
Did you have to start at a flat rate of 10?
Okay, well let's start with 10s. So we have 10, 20, 30, 40, 50, 60, 70, 80. And so those are dollars. That's how much it's going to cost us. All right, so off to the side, let's just kind of make a table, okay? If I don't buy anything at all, technically they're still going to charge me how much if I call them and say, I want to buy 0.
$10.
They're going to tell them $10. Every order they take is $10 no matter what. So that's going to kind of be our starting point. if I buy half a box, they're still going to charge me what? $20 plus the 10. So they're actually going to charge me $30. What if I buy a whole box? Still going to charge me $30. Okay. What if I buy 1.5 boxes? They're going to charge me as if I bought 2, right? So that would be $40 plus the 10 I have to pay. So that would jump up to $50. Okay. Well, that would stay true until I hit how many?
2.
That would still also be true for 2 boxes. That would charge me $50 as well. All right, let's go and see what we have graphed so far. At 0, they're going to charge me $10. Agree? But at half a box, it jumps up to 30. A quarter of a box would be 30. And, 8/10 of a box would be 30. So everything between 0 and 1 would be 30. And 1 box would also be 30. So notice that the closed circle is on the right side rather than the left side in this case. This side over here is where it makes its jump. So we'll put an open circle there. So depending on how the problem is worded, the open circle could be on the left or on the right. Here it's on the left, but on the greatest integer function, it actually always ends up being on the other side. So you have to be real careful with this. All right, then if I buy 1.5 boxes, they're going to charge me $50. If I buy 1.2 boxes, they'll charge me $50. And if I buy 2 boxes, they'll charge me $50. So everything between 1 and 2 boxes gets charged for 2 boxes. So obviously it's making how big of a jump every time? $20 more, because that's how much more they're charging me for every box, right? So then this one will jump to 70, and we can guess that it would stay here for the entire time. So that's kind of how you look at some business applications, and then you can kind of read the graph and figure out what's going on at a set number. Any questions about that, Stowers? You're okay? Everybody else okay? All right. Even though technically this is the end of the line for this section, I'd like to make up a problem and have you look at it, okay? Let's say that at this point, I would like you to evaluate. What's evaluate mean? Evaluate means give me what type of an answer. Does anyone know? A number answer. I'm looking for a number answer. I would like you to evaluate the piecewise function f of x equals 2 times the greatest integer of x minus 5. It's a tricky one. For the values of 3, of 1.7, and negative 2.8. So I'll pause for a minute and give you a chance to kind of talk with each other, see if you can figure out what those 3 y values would be for that function for those given x values. All right, for the first one, if we want to find f of 3, that means I would like to let x be 3. So I have 2 times the greatest integer of 3 minus 5, which is 2 times the greatest integer of negative 2. Well, what's the greatest integer less than or equal to negative 2? So really I have 2 times negative 2, which is negative 4. So that's the long way through it, right? That's what you guys all told me. What did you get for f of 1.7? Ooh, we're hearing different things. We've got a negative 6. We've got a negative 8.
I got negative 6. It's definitely negative.
So we got to decide. It's somewhere between negative 6 and negative 8, right? All right, let's see what it is. If I substitute 1.7 in for x, I get 2 times 1.7 minus 5, which gives me the greatest integer less than or equal to, what's 1.7 minus 5, guys?
Negative 3.3.
Negative 3.3. Okay, what's the greatest integer less than or equal to negative 3.3?
Negative 4.
Yeah, you have to be really careful with those. Because if you're looking if you're looking at these, this is -3, this is -4. The smaller of those is what you want. It goes to the smaller one. It brings it down smaller. So that makes it -4. So 2 times -4 is -8. And finally, what's f of -2.8? Ooh, we're still hearing them. -14, -16, -16. Okay, let's check it. Alright, so we have -2.8 minus 5. Now, inside this greatest integer function, that cleans up to -7.8. Agreed? So I want the greatest integer less than or equal to -7.8. So it's either going to be -7 or -8. Which one's smaller? -8. So it's going to go to the one that's smaller. So that's really going to be 2 times -8, which is -16. And that wraps up section 3.3.